This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here today with Aubrey Clayton, who teaches at the Harvard Extension School and is the author of this book I have with me right here. It's called Bernoulli's Fallacy, Statistical Illogic, and the Crisis of Modern Science. Aubrey, this book is kind of like it's like a bombshell in a sense, because you make some very, very bold claims. I've been teaching statistics for 30 years, right? And, I teach hypothesis testing and inference and all the stuff that makes up the core of, traditional statistics. And this methodology lies at the heart of pretty much every type of science out there, in particular in the social sciences and psychology and so forth. It's become the norm, and you argue that it's really sitting on fundamentally faulty foundations, and that it needs to be overhauled, if not completely rejected. And I think there's a lot of people in the sciences that know that there's a problem. I mean, I think there's a lot of people that know that it's a flawed methodology from the get-go, and so, but they don't want to reject it. They want to kind of, maybe reduce the p-value or, do pre-registrations. Sure. Or, there's all these, we might call them Ptolemaic curlicues that we have to add to the methodology to kind of keep it going. And you argue that, well, why not just ditch the whole thing and switch to this Bayesian approach? So, so maybe we can just jump right into it and, talk about what exactly is the fallacy, the Bernoulli fallacy, which sits at the heart, at the origins, at the very beginning of, this methodology that we're applying to pretty much everything we're trying to understand about the world.
Sure. Yeah. Well, so I think, first of all, I completely accept that framing. I think that this is a radical proposition that I'm making. In a way, I think it's timely because, as you alluded to, I think a lot of people are receptive to the idea that something is fundamentally wrong with statistical methods. And there seems to be evidence in what's going on in the sciences that is having real repercussions. And so I think it's an opportune moment to be kind of thinking about these things. And it's definitely the case that most of the dialogue around methods has been kind of marginal improvements and maybe tweaks to p-values, or using maybe the existing methods in a slightly more scrupulous manner, or other kinds of like scientific methodology improvements. But I think what I'm suggesting is basically there needs a radical overhaul, that we really do need to kind of rethink the whole scheme and effectively throw out probably 90% of what is taught in the kind of standard statistics curriculum. So yeah, it's a radical proposition, but I think it's also, in some ways, it's an old message, and one that goes back to some of the debates that have been around, that have been present around statistical methods for as long as they've been around. So I don't think I'm really saying anything too new, but maybe I am bringing back to the surface things that have been dormant and have been kind of lurking. But to get to, I think, really the heart of the matter, which is the title of the book and the fallacy that I think is really what underlies all of these problems in statistics. So what I describe as Bernoulli's fallacy is the idea that you can make good decisions about hypotheses, scientific hypotheses or statistical hypotheses or just research theories in general, using the language of probabilities, but focusing entirely on probabilities that are oriented in the direction of, if a hypothesis is true, then what is the probability of some observation or some data? Right. So these are what I in the book call sampling probabilities. And they're the kinds of probabilities that people are very adept at manipulating and doing calculations on, because they're basically the kinds of things that have to do with observables, right? If you have an experimental setup what's the probability that you get a certain outcome, and you can kind of put that in frequency terms. And basically what I want to argue in the book is that is not, that's not enough ingredients to make good inferential decisions about hypotheses. What you really need are the probabilities that go the other way around. Given some observation, given some data, what probabilities do we associate to, or do we assign to the research theory, the hypothesis, the experimental, setup, whatever's driving it. And basically we need to reverse the direction of the probabilities. So Bernoulli's fallacy is the idea that you can somehow get from one to the other, that if you have enough of these sampling probabilities, you can assemble them into kind of a good decision-making framework. And it's just not true. It's not possible.
Yeah, I mean, this is, I think when you're teaching statistics, you run into this problem right away. I mean, you just get a question from a student, right? And they say, okay, I get it, right? Like, if the world looked like this, hypothetically, then the likelihood of getting this observation is this, okay? But, what do we know what the world actually looks like, right? We see this sample, and we're trying to what we're really trying to do is figure out what's really going on. And, what's that probability? And, the instructor has to say, well, I can only, we focus on calculating type 1 probabilities because that's like, we know how to do that. Right? And what you really want to know is type 2 probability, but, we don't know how to do that. So we're just not going to do it. So, let's just move on. Like, next question. Right. So, I think everyone who does statistics kind of knows that this is a problem, but we kind of push it under the rug just because, we really don't know how to do it. So we focus on what we do know how to do. And the part that we do know how to do, maybe because you talk a lot about the history of statistics and probability. And, it was all of these theories evolved out of basically games of chance, right? Where the fundamental underlying probabilities were known, right? Or at least were, believed to be known. So maybe you could take us back to the history and how this whole way of thinking about the world emerged.
Yeah, sure thing. And I think it definitely, the confusion about these different types of probabilities and the roles that probability play in this kind of inferential framework. I think what's kind of exciting about this in a way is that you can see exactly the same confusion 300 years ago that people are experiencing now, right? So when you talk about, people kind of understanding that this is a problem, and when you teach stats, you kind of experience the confusion that students have over this. The reason they're confused is because it kind of doesn't really make sense. And that mixing those things up, I think, has a very long history. So the reason I call it Bernoulli's fallacy is that, what really kind of drove me to tell this historical story was reading the work of Jacob Bernoulli, who is one of the kind of founding fathers of probability and statistics. And he was, at the time, he was responding to this kind of new discipline of probability, which had emerged, just as you said, to handle games of chance. And so kind of had this demonstrated success in solving gambling disputes, in kind of dice games and things like that. And his ambition was to basically take the success of probability from those domains where it does work really well, and you can think about it in these kinds of very objective and observable and measurable terms, and to extend it into things like economics and social science and the law, and basically use it as a framework to make decisions about all kinds of things that had nothing to do with gambling games. But he thought that he basically had a mathematical tool that allowed him to do that, which is his famous law of large numbers, what he called his golden theorem, which, if you look at it in kind of just the right way, it does seem to be doing the thing that I said was impossible, of answering a question about inference using only probabilities that have to do with data and observation. And so that mistake that he made, which, I kind of discovered, and I mean, I think that I'm not the first person to say this, obviously, but I arrived at, and I noticed, and I kind of got immersed in when I was reading his work, it really does carry through to modern day statistics, and particularly in the work of people like Ronald Fisher, who kind of built what we think of as the orthodox statistical framework that we use today. So it is a way, it's a very old story, but it's also very contemporary. And I think that's when you kind of see that continuous line, it's very exciting.
Right. And so the goal is to create sort of a way of understanding the world, of making inference about the world that is not tainted by, biases and prejudices. I mean, I always think of the methodology, right, of hypothesis testing. We try to set up a test which goes contrary to our assumptions, right? In other words, the burden of proof is on the thing that, we're trying to show. And so it seems to me that this is designed to be an intellectually honest way of operating. So if we go to the famous Darrell Bem study, right? And I remember when this came out, and I remember talking about this in class, right? Immediately when it came out. So Darrell Bem is the professor at Cornell who seemed to demonstrate that, psi or, ESP was real, right? So the null hypothesis was that it's not real. And then, we get all this data, which seems to show that, it is real, right? And so he submits it for publication, and, as a juror, right, of one of these publications, you're not supposed to let your bias enter into the evaluation process, right? Now, so look, you don't believe in ESP, I don't believe in ESP, so we're supposed to. But we're supposed to ignore that and say, well, the data speaks, right? We set up the methodology before we know what the outcome is. We get this outcome. And of course, a lot of people were kind of outraged, like, well, this is like submitting an article proving that, leprechauns hang out underneath mushrooms, right? Because, it seems to be in the data. And so I think that when that was published, all of a sudden, people had to confront whether or not they should, let their priors into the discussion. And I think that what it revealed is that people are doing it, even though they say they're not doing it, right? Because what happens is that we say, well, I think your sample size isn't big enough. Like, let's run this again. Whereas if it confirmed what we already believed, we would have been like, great, this is fantastic. We're done here. Let's move on, right? Let's go to the next subjective inquiry. So one of the things that I think the point you make is that you can't really do statistics without assumptions. So let's bring them out into the surface and force ourselves to articulate them, right, in the form of these priors. Maybe talk a bit about, I mean, when you first, I don't know which the sequence was, when the BEM study and when you kind of came to this conclusion, because that really does, I think, highlight the one of the key problems that we're faced with.
It really does. That BEM study that's now been just over a decade since it came out, but I think it really did ignite a lot of the controversies about the replication crisis in science, and a lot of the kind of introspection that the scientific community has had to do, because just like you described it, essentially that was a study that obeyed all of the rules, right? Statistically speaking, it followed all of the procedures, and it was in every way, pretty much by the numbers, social psychology study. And yet it came to this, what we should understand as an absurd conclusion, that ESP is real, in particular that, college students can anticipate random numbers, but only if it has to do with a pornographic image, because that is, according to BEM's research theory, an evolved precognitive ability to anticipate sexual opportunities. And so there's a kind of a story behind why that particular kind of clairvoyance could exist, which is something we should just be willing to throw that out on its face. But I think it's challenging in a way to see just how normal that study is, and how the data analysis is pretty standard. So I think that is a case study in maybe what's wrong with these methods, that they allow, studies like that to be published, and they don't give a language and a framework for expressing skepticism about those theories ahead of time. Okay, so the alternative, and what I argue in the book is needed, instead of this Bernoulli's fallacy direction of only thinking about probabilities of the data, was we have to be able to turn around and talk about the probabilities of the hypothesis. Well, in order to do that, you need to have your prior probability assignment. You need to know what background information you bring to the table about a research theory before you start evaluating the evidence. And the standard methods of statistics just don't include that. They don't at any stage of the inferential analysis explicitly call out what your prior assignment is to the probability of a research hypothesis. But I think just the way you said it, those priors are part of our reasoning, even if we don't admit to them. So when we look at a study like that, like BEM's study, and we say, we don't accept that, or and we look at other studies and say, okay, that seems more likely, that accords with our prior understanding of the world, we have done a kind of sorting into what things we had a prior probability of being true and what things we didn't. And I think, some of the proposed remedies to get around that, they are just missing this very important question, this kind of what I would call an essential ingredient. Anytime you're evaluating data, in an experimental setting. So, a lot of people might say, well, the problem with that study is that it didn't pre-register its hypothesis. Well, that's fair in a sense that he probably did tailor the hypothesis to a degree to the data, but reviewers, when they register objections and come up with alternative explanations, they didn't pre-register their objections either, right? So we do allow for that kind of post hoc theorizing when it comes to, coming up with other explanations for the data like that. So that's probably not really the right answer. It could have been that he pre-registered it and he would have gotten the same data and he would have published it just the same. Really, the answer is, I think that the meat of the answer is, this is a theory that contradicts our prior understanding of the world. That we don't believe that people have this ability. We don't have a physical model of how this could work. We have lots of prior evidence that it doesn't exist. And so even somewhat, convincing, persuasive evidence should not really move the needle very much in terms of our probability assignment of that theory. Maybe a little bit, but we should have a language to express that prior skepticism. And that's what Bayesian statistics provides, that the standard methods just kind of don't.
But isn't the standard method, though, isn't it sort of a noble idea, right? That we should abandon all priors, right? And be prepared to accept things that are counterintuitive, right? I think if you think that the problem is biased reasoning, if you think that the problem is confirmation bias, right? If you think that the sun goes around the earth, and and no matter what evidence you see, you're gonna say, well, that's not good enough, right? I need more evidence. Isn't that kind of the thing that the scientific method is supposed to kind of abandon, right? And say, look, if we're gonna believe a process, and then whatever comes out of that process, we just have to believe it. Isn't that what science is all about, right? And doesn't bringing kind of priors into the equation open the door to all sorts of kind of confirmation bias and prejudices and so forth?
Well, yeah, I think that there are definitely some noble ambitions there, and I don't want to discount the importance of skepticism. I think, as I say in the book, the great promise of science is that it is a disciplined and organized framework for skeptical thinking. And I think that is essential. Anytime you have an experiment or you have observations and you're trying to maybe justify a theory, that someone should be asking the what if question. What if there's another explanation for that? And what maybe latent assumptions are we making that have driven us towards looking at the data in this way? I think where I kind of get off the train there is that I think that the statistical methods of, the 20th century essentially tried to make a false promise that you could do inference without any kind of prior assignments or prior assumptions or subjectivity. And I think that, basically the way that these methods have been advertised is as a kind of perfectly objective, crystalline method of processing your data and turning it into a conclusion that is somehow free entirely from input on the part of the experimenter or on the part of, the person doing the interpretation. And I think that is just never how science has operated. And it's not even it's neither an attainable objective, nor is it even desirable, as a kind of framework for making sense of observation. There's always going to be judgment. And I think it should and can include skepticism, but it's never going to be just, put the data into the hopper and turn the handle and out comes your conclusion. And I think that even, in the work of the people who developed those methods, you can see how they were injecting their own biases and assumptions and their prior understandings of the world into their data analysis in the course of using those statistical methods. And I think, really what I'm arguing for is just making that more explicit, making the implicit explicit and saying, this is what I bring to the table, when I do an analysis of the data. This is my previous understanding of the world. These are the probability assignments I give to these different theories. This is my prior distribution. This is what the data tells me. This is how I update it. And maybe that you would get a different answer because you have a different background and somebody else would maybe come at it with a more skeptical background. And together as a community, we can reach consensus about what the data is telling us. But it is not at any point just kind of free from our input and something that the numbers and the data just kind of speak for themselves. I think that is really a dangerous idea. And it's something that's really at the core of the kind of scientific philosophy in these methods of statistics. So that's really what I want to challenge.
Well, I'm wondering if your insight is in part a product of the education you got and the trajectory that you took for learning. I mean, you're a probability theorist, right? I mean, this is what you studied, and I think when you were in grad school out here at Berkeley, you did a little bit of gambling right, on the NBA games, right? I don't know if you still do that, but you entertained the hope that you might actually retire early from your gambling winnings.
Yeah, I should interject that I did that at a time when it was legal, and it was made illegal by act of Congress about 1 year after I kind of discovered this profitable gambling opportunity. So that career got shut down by law, and I obey the law. So just for complete clarity.
Right. But we talk about probability and statistics, and when we teach statistics, we ground it in probability. But you kind of, went from probability to statistics. And what like when you encountered sort of how people were using statistics and how statisticians talked about probability, I think you found it a little bit unusual, right? Because it seemed a little bit counterintuitive to what you had learned as a probabilist, probability theorist, right? Can you talk a bit about that journey and how you kind of went from probability theorist to commentator on how scientists use probability?
Yeah, sure. Well, I think, a major question that I think is really, at the foundations of the statistical methods when you really dig down deep enough is just that question of what is probability anyway. And I had studied probability in the kind of mathematical sense for several years. By the time that I got to grad school, and I really kind of became aware of these issues. And I think what's interesting about that is that you can study mathematical probability without really ever having to confront that question of what probability is, because in a mathematical sense, we know what it is. It's, probability measure on a sample space, sigma algebra of events. And going from there, you can build a lot of kind of very beautiful mathematical structures on top of that. But that doesn't really help you if you're going out into the real world and you have some data and you're trying to make sense of it. And so what I think, I was really kind of struck by is that in all of that probability theory, you're always given the probabilities from the start. Right? You have an assumption of a probability measure or a set of probabilities, and then you're basically just asking about the consequences of that, of those assumptions. Mathematically speaking, how can you manipulate those probabilities? Where really, what's needed in a kind of real world sense is identifying a probability, assigning a probability, and the math just doesn't help you with that, right? So if you want to know what's the probability that someone's going to live for 10 years, or what's the probability there's going to be a major earthquake, you don't have a mathematical way of assigning that. And so I think you have to start asking this question of, well, what is probability then? If you, are you trying to observe it in the real world? Are you assigning it based on information? Is it something internal to you, or is it something, external? And I think that, basically, when you come to do statistics, you have a very real problem if you haven't sorted out in your mind what you understand probability to be, right? So the essence of this kind of Bernoulli's fallacy, I think, is it gets back to a desire to make probabilities observable and measurable, basically in the form of frequencies. So you want probability to be about how often something occurs. Like, how often do you get, a royal flush when you deal a poker hand? When probability has to mean so much more than that. If you want to use it to make inferences, it has to be able to, to apply to hypotheses or one-time events or things that happened in the past, and things that just don't have a natural kind of frequency meaning to them. And so the traditional kind of answer to the question of what is probability, that it has to do with frequencies, is just inadequate, right? For all the ways that probability is really used and the role that it has to play in scientific decision-making. So I think, what needs to happen to kind of fix these methods is we need to get back to that question of what is probability. And we have to come up with a form of probability that has all the mathematical properties that we want it to have, but that also is usable in the sense of, applies to all these different settings where you need to assign probabilities to things. And I think that the answer to that is basically that probability has to do with information. Okay, and this is a fairly new sort of idea, and mostly present in the writing of someone named E.G. James, who I don't know if he's gotten quite enough attention or as much as he deserves. But I think, much of the inspiration for the story that I tell in the book has to do with the James form of probability as information, and as reasoning under uncertainty. And I think if people kind of adopt that framework, then a lot of these questions start to become more clear.
Now, of course, I think at business schools, we've introduced data science as a discipline, right? And the traditional inference is kind of taking a back seat, right? We're kind of, moving past it. And one of the criticisms of data science is that if you don't have a foundation in statistics, then, you're likely to make all sorts of faulty inferences in data science. But is data science in some ways kind of an improvement over kind of traditional inference in the sense that, we don't really emphasize statistical significance as much, right? I mean, I like to say that if you needed to have statistical inference, if you needed to have a p-value below 0.05 to, justify getting out of bed in the morning, like you'd never get out of bed, like, like 99% of the decisions that you make on a day-to-day basis are not based on any kind of statistically significant, hypothesis test, right? And similarly, business people are making decisions all the time. So in some sense, data science is an improvement because it abandons a lot of that clunky machinery, but it has sort of problems of its own. Do you think that the move towards data science is kind of in many ways an improvement when it comes to. I mean, data scientists aren't really sometimes they say that they're not really trying to uncover any kind of truth about the world. They're just trying to, provide good, predictive models, right?
Mm-hmm. I think that's true. I think it, in some ways, it cuts both ways. So I guess I wouldn't be too committal in really calling an improvement or another. I think, or not an improvement. I think it's good in a way that data scientists have abandoned the clunky machinery of significance testing and ordinary statistical techniques. I think there is definitely a need for some more maybe slow thinking about the nature of probability and what role probability is playing in those kinds of data science models, and basically what can be going on in the data that your model may not be accounting for. So I think, there are definitely foundational and important questions that people should be spending time thinking about. And I think that Bayesian inference does have a lot to offer in terms of helping provide a solid foundation for that. So I think, if you're going to be doing data science, let's say, and you have some, very complicated, neural net model or something, ultimately, if you're training that model and taking, values of the parameters of that model from some training data, really you should be assigning probabilities to those. You should have prior distributions for those parameters. You should be looking at uncertainties around those things, and that you should have kind of a Bayesian paradigm underlying that inference or that that model fitting exercise. And then you should also be thinking about problems with the data and alternative explanations for any kind of patterns or associations that you're trying to make. So I think there are lessons to be drawn, but at least I think it's a good start that you're not using p-values. So good on you.
Well, one of the improvements I remember when I first encountered the confusion matrix, I remember thinking, oh my gosh, like this is, how could I have gone through my entire life, without having a confusion matrix as a way of understanding what we're doing. And I still encounter all sorts of social scientists who are designing experiments, and they don't include any kind of confusion matrix because they create an artificial kind of base rate, and then they don't think about how that transfers over into the real world with real world base rates. Could you jump in and talk a bit about the replication crisis? So, we mentioned the Darrell Bem study, but that's really only the tip of the iceberg, right? We've been seeing all of these studies get questioned in all of the sciences, particularly in the social sciences. And we start to realize that the ones that get published are the ones that are actually the most likely to be kind of rejected or refuted or, failed to be replicated.
Yeah, I think that is a disturbing pattern. I mean, I think, so the replication crisis really started in psychology and results like Bem's. And I think that caused a lot of, as I said, introspection about previously published results that had never really been replicated or had been never attempted to be replicated. And so there's been large-scale efforts in lots of different areas of science in the last decade to just try to examine things again and maybe run an experiment with the same original materials if you can find them, and more participants and maybe higher power in the statistical sense, and just see how you do. And I think that the emerging trend that I write about, and that I think is kind of becoming clear, is that something like half of scientific results just don't hold up when you try to replicate them. And that is, many different possible definitions of what it means to replicate. But I think basically, even in a high-powered replication, having a statistically significant result or effect in the same direction as the original is sort of maybe a reasonable standard replication. Something like half of results just don't meet that standard, which is disturbing. And among the ones that do, it seems to be that the strength of the effect or the association is also overstated by about a factor of 2 when you do the replication study. And this is something that doesn't seem to be isolated to one particular scientific domain or another. So, psychology, I think, has produced the most visible examples, and in some ways the most kind of media-friendly examples, particularly social psychology, which is, very kind of vivid and narrative. But it's the same pattern seems to have emerged in, social science more generally, economics, also neuroscience, preclinical pharma trials, cancer biology, medicine, basically everywhere. And I think that for me, the common kind of thread is that all of these different domains have relied heavily on statistical techniques. In particular, null hypothesis significance testing has been the common language of inference for about the last 100 years. And so it's not surprising to me that you see the same kind of problem manifesting in all these different domains that have used that same kind of scientific statistical language. And for me, it gets back to the fact that there are a lot of theories that are being published because they meet a statistical standard of significance, of acceptance, but that should never have been entertained because they should have a low prior probability and a low posterior probability of being true after interpreting the data. So I think basically having that kind of skepticism filter would have helped keep out a lot of these false positives. And I think that unfortunately there's kind of a bias in the other direction where results that are novel and unexpected and challenge maybe an existing worldview tend to get more attention and more, maybe are more likely to be published because they are exciting in some way. And so I think people are drawn to kind of investigate those theories because they're if they pan out, they're going to be rewarded. But I think it's unfortunately created a kind of perverse incentive to be looking at theories and research questions that really we should, maybe not be so dogmatic as to say they're impossible, but we should raise the standard of evidence to say, okay, if you want to argue that, holding a pen in your teeth makes you happy because it forces your face into kind of a smiling position, then you're going to have some very impressive evidence to convince me of that, because that is something that contradicts my prior understanding of the world, contradicts my kind of theoretical background.
But sure, but when I hear the explanation for it, it sounds totally plausible. And so my prior might be, well, if you told me the story, like, hey, embodied cognition, smiling makes you happy, then all of a sudden that would be my prior. And so I wouldn't examine the results too carefully because I'd think, well, okay, that lines up kind of with what makes sense to me. Do you think that the publication of kind of provocative hypotheses is just a byproduct of the adoption of this methodology, or is that kind of the point, right? In other words, how do you explain the kind of emergence of this methodology and kind of a consensus around this methodology when we've had this kind of Bayesian approach kind of in plain sight for ever since Thomas Bayes, right? I mean, we've had an alternative way of thinking about inference that's always been there, and whether Jaynes articulated it or not, right? It was always there, and so it's kind of even though it may not be explicit in scientific method, it's certainly implicit in the way ordinary people go about their lives. So why How do you account for the consensus around the hypothesis testing methodology, even after all of the problems with it have been articulated through this, replication crisis?
Mm-hmm. Yeah, well, that's a very big question. I mean, I think, the story I try to tell in the book, really about the victory of frequentist statistics and what we now kind of think of as statistical orthodoxy. That happened in the mid 20th century, and in large part due to the influence of Ronald Fisher, who was just one of the dominant figures in developing those methods. Mm-hmm. I think up to that point, you're absolutely right that Bayesian methods were around. They, at the time they referred to it as a method of inverse probability, and that was exactly, functioning in the role that I described of turning the probability statements around from data to hypothesis. And people, I think, understood that was the direction that they cared about. There were definitely problems with it. And I think that there are definitely very difficult to answer questions about Bayesian inference that have made people uncomfortable for as long as that's been around. And so, there's a long and storied history of criticism of Bayesian techniques, particularly assigning prior distributions and what does it really mean? Where do these priors come from? And so I think that kind of debate was still vibrant and present up until the time of Fisher. And it was Fisher who really said, actually, there's a way we can get around all of this because these methods that I've come up with, particularly significance testing, maximum likelihood estimation, and fiducial inference case, kind of big contributions, they sidestep that whole debate because what they do is allow you to do inductive inference and only rely on the probabilities of the data, which are empirical and observable frequencies, right? And so we can turn things around. We can use these ingredients and build up good inferences from them. And I think that, again, as a kind of, historical context for that, what you have to understand is that Fisher and others were developing those techniques to answer questions in a very controversial setting. And they were basically trying to develop, the theory of evolution, as the kind of first test bed of these statistical methods and looking at data of different species and understanding, is there evidence that this comes from one species and this comes from another species and that evolution is at work. And that was very controversial. And they were also deeply involved in the eugenics movement. Fisher's predecessors, Francis Galton and Carl Pearson, were major advocates of that movement. And so they were basically arguing for some very drastic social propositions about, limiting the size of families and incentivizing people of kind of high social status to have more children and disincentivizing other people against having children and limiting immigration and trying to identify kind of racial differences between subpopulations in society. And so these were things that had very high stakes for them. Okay, they thought that basically all of society was riding on these conclusions, and they wanted them to be unassailable. They wanted their conclusions to basically be apparently just a pure product of the data. And so I think that, the kind of authority that they sought out was to argue for those positions and not have their prejudices seem to enter into it at all. To basically say, look, the data is speaking for itself. These Jewish children just aren't as smart as the non-Jewish children or whatever kind of theory they were advocating for. And I think that is the kind of the false promise of statistics, and is kind of the tempting story around statistics that is still present to this day when we say, look, the data is just telling me what it is. This isn't anything to do with me as the experimenter. I just ran the experiment and it turns out you can make yourself happy, or, this gene is associated with this disease. And so I think that is basically where that Faustian bargain kind of originated. Mm-hmm. And it made sense at the time, given the kind of the scientific and the social agenda that those statisticians had in mind and were working towards.
Now, of course, a Bayesian approach wouldn't kind of fix that problem if those priors were generally accepted, right? Like if most people bought into those priors, then a Bayesian approach would probably entrench them even further, wouldn't they?
Well, it's entirely possible. I think that it gets back to the question from before of the role of skepticism, mm-hmm. And consensus. So, I think that you're right in a sense that, if the common view, the kind of consensus prior is that an explanation is particularly likely, and then the data seems to support that. If everybody's on board with that, then probably Bayesian methods are going to support that conclusion. Mm-hmm. I think that that's where there's still a role for skepticism, and I think people should be continuing to ask the what if question of, well, okay, but where did that data come from? How are we measuring intelligence, or how are we assessing the differences in these groups, or is it really biologically determined, who's successful and who isn't? And I think over time, ultimately, the data will support an alternative explanation. Right. So I do believe that there is truth in the universe, and I think that Bayesian reasoning will ultimately converge on that. But I think there are lots of famous examples in science of experimenters basically being surprised by their data, or drawing a conclusion from their data that is actually not, what stands the test of time. And that's fine, from a Bayesian point of view, that's fine. And all I think that we can really do is try to make our assumptions explicit and say, mm-hmm. This is where I'm coming from. This is how I understand the data because of this prior understanding I have of the world. And to say, well, actually, it's not about me, it's just the data. I think that is the dangerous myth of inference that then, enshrines these kinds of conclusions as kind of scientific truth, to say, no, this has nothing to do with our situated knowledge of this, the data generating process or how these things were measured. This is just the numbers, and right. It just turns out that things are the way they are. And I think that, to get back to the question of data science, I think that kind of attitude of almost humility is probably what's needed more in data science today. Because I think that without that kind of understanding that any conclusions you draw from the data are a product of your prior understanding and your prejudices, you will be inevitably led towards, doing some pretty awful things with your data and kind of accidentally reinventing things like eugenics and phrenology and all these other, horrible historical phenomena. So I think that's where the Bayesian framework really has something to offer. It says, okay, you can make that conclusion, but at least you have to be upfront about your prior probabilities.
So now I think everyone has a belief that the solution lies in transparency in the methods section, right? And saying, well, I thought I'd find this, and then I found this, and so I ran another test because I wasn't happy with the first test. And as long as people are completely honest with respect to, the file drawer and so forth, that we'll get to proper inference. And you're saying, well, that's great. We need that. You have to have that, but you also need to, articulate what your prior beliefs are before we can really understand the impact of your study. And you introduce a methodology, right? So you're not just simply saying, hey, put your priors out there. You're also saying that we can look at an individual study or test and kind of measure its impact, right? In terms of how much it moves the needle on our understanding, right? Mm-hmm. Could you just talk about briefly, what that approach would look like and how that would affect presumably a whole lot of things that get published today would not get through that filter that you've proposed.
Yeah, I think, in a way it's interesting because, certainly a lot of people have identified this problem of publication bias as a major driver for, what's going on in the replication crisis. And I think that there's certainly something to that. I think, what I'm offering or advocating for, in the kind of Bayesian framework is a greater transparency about your theoretical reasons for asking the question in the first place. Just as people are asking for more transparency about your methods, how did you get the data? What did you do with it? Why did you analyze it whichever way you did? And also, how many times did you do it previously? And what other experiments did you run that you haven't published? And I think that, having as much transparency as possible is good. And part of that transparency is, well, what prior experiences have you had that might make you think that there's a theoretical reason to expect, the data to support this answer or not? And what prior probabilities do you assign to it without even having seen the results of your experiment? So I think that, in a way, again, it's a useful vocabulary for bringing or for making everything explicit that you're bringing to the table when you do an experiment. But I think that the other side of that, and a kind of another useful conceptual framework, is that we never have to answer questions definitively. And I think that the hypothesis testing framework, again, has this very binary feel to it of something
you
being
reject the
significant
null,
or not
or you
significant.
don't reject the null.
You
right?
reject it. Yes, exactly. And I think,
there we've
Fisher
proven, right? We've
yes,
proven
right.
this.
And
right?
and it feels like you've definitively established something, right? When you identify something significant, or in Fisher's case, he said you never disprove the null, but you can ignore experiments where a significant result is not attained. So basically, you can you disprove the null. And I think that getting out of that binary mindset is also very important here. So in the Bayesian framework, again, you start an inference with a prior probability, you interpret your data, you come out with a posterior probability, and that's not the end of the story. That posterior probability can then serve as the new prior for a second round of experiments. And so, what I say in the book is that, a lot of people want to do meta-analysis as a kind of way to sort out these replication problems. But in a Bayesian framework, every analysis is a meta-analysis because, when someone has done an experiment, even if it's got a single data point, it moves the needle a little bit. And then that can be the starting point for an analysis of a new data point. And every time you get more evidence, it's kind of incrementally, moves your probability assignments. And eventually you might say, okay, we're near certain that this is true. But at no point are you declaring it yes or no, definitive or not.
But that would mean that we would have to, tenure. You could get tenure for publishing a whole bunch of papers that don't say anything new, right? I mean, because if you're doing a meta-analysis and you're only doing a meta-analysis on the things that are published, then you're basically, basing it on a very, very small subset of what, presumably would have been uncovered if you ran a whole bunch of other tests, right? So we need to change the reward system in academia so that, if I publish something that says that, 2 + 2 is 4 and that the earth goes around the sun, like, that I've got to get credit for that. I've got to, get tenure for that. Right. But that's not how it works right now. You get tenure for the cool stuff, the surprising stuff, the counterintuitive stuff. Right.
Not being tenured faculty anywhere, I think I can agree with that. And, maybe other people would tell me that that's misguided. I think that there are definitely institutional incentives that are causing a problem here. And the ways that people's careers are determined by, the results that they publish. And, whether their findings were significant or not. I think that is unfortunate, and that also needs to change. I don't know if I can prescribe a complete answer to that, but I think that there's something valuable about contributing evidence even to support theories that we think are already true. And I think it's part of the problem with these replication studies as well, that it's hard to incentivize people to do replication work because in a sense, you're just repeating somebody else's experiment. And there's very little kind of to be gained personally from doing that, especially if it fails. But I think everyone who does a high quality experiment like that is contributing something to the body of scientific knowledge. And I think, going back to some of these historical examples, what you'll see is that sometimes, what was really needed for a theory to really take off was just a very high quality, well-designed experiment that maybe validated something that people already believed in, but that did so in a way that was novel or really, contributed something to the techniques of that scientific domain. So I think, there's lots of opportunity for reform here. And I don't know really all the answers, but definitely getting away from the kind of tenure reward system for new findings that just reach a significance threshold. That's got to change. Absolutely.
Okay. So as someone who teaches statistics and has taught for 30 years, how do we need to reform our classes? How do we need to change the classes that we teach, not only to kind of, business students, law students, right? Social scientists, natural scientists, right? Everybody who's doing empirical work has the same kind of training in hypothesis testing and, classic statistics. What would those courses look like if we were to take seriously what you're arguing in this book?
Yeah, well, I think for one thing, they would be a lot shorter. So I think the first thing that we need to do is just get rid of a lot of that infrastructure of hypothesis testing and all of the standard kinds of tests, anything that has a p-value with it, and also just to change the whole or eliminate the whole framework for how we understand the results of a test or of a regression or an analysis of any different kind. So I think, if you start removing things like null hypothesis significance testing, p-values, unbiased estimators, consistent, robust, admissible estimators, get away from kind of all the long-term properties of estimators and the convergence properties of regression, then basically you're left with very little, which is good, because I think probably what we should spend much more time talking about is just the fundamental question of what is probability anyway, and where does it come from? And I think that, most treatments of that basically try to sweep that under the rug, because they start off with some very cursory introduction to probability and say, okay, probability means likelihood, and you have the sampling space, and then you're talking about events that are subsets of the space. But you have to have the assumption that all of those events were equally likely to begin with. Mm-hmm. And so what does it mean that are they equally likely, or are you assigning them equal probabilities based on some information you have about them? And that question we need to slow down and really spend some time answering. And then, all the things kind of flow from there. So I think once you have this idea of probability as having to do with information and kind of reasoning under uncertainty, then you'll see that Bayesian inference is really the only kind of inference that we should be using. And so then the whole question is just about assigning priors and likelihood functions, and then doing Bayesian inference and having your posterior distribution and maybe the computational techniques that are associated with that. So I think, what we should do is first clear some space and then focus on those very real fundamental issues.
So I presume this would also divert more resources to kind of the development of structural models, right? So, I think in finance, so much of finance is built on, like you say, hey, we've got 100 years of data. Next year, the results are likely to be drawn from a random sample made up of the last 100 years of data, right? And that just seems implausible from beginning to end, right? That the last 100 years is somehow some stable process that generates kind of returns in financial markets and so forth. And yet, that just seems to, we have an entire edifice that's built on top of this very crude and unrealistic assumption. And maybe if we're forced to dig into those assumptions a little more aggressively, we might abandon everything that was kind of stacked on top of that and think more seriously about kind of structural models of what's going on.
Yeah, I think that might definitely be the effect of rethinking things from the ground up. I think the other, maybe the key framework that people should be thinking about a lot more is causal inference, and just what are the kind of causal connections between the things that you're observing and the kind of latent variables that might have an effect on your observations. And so, I think Richard McElreath, who wrote Statistical Rethinking, said something very astute, that basically he could spend the rest of his career just explaining collider bias to people, and that would be a worthy pursuit and a contribution and a good use of his time. That I think people are not fluent enough in the vocabulary of confounding variables, collider variables, kind of Bayesian causal networks and acyclic graphs, and basically using your domain expertise and your understanding of all the different variables that are at play in your data to come up with a model for what influences what, and what you might be able to observe, and what things you should control for and what things you should definitely not control for, because they're telling you an important story in your data. So I think that is again something that gets just completely ignored in the standard statistical framework, because you throw everything into a regression model and you say, okay, I've controlled for it. But the question of, well, what causal relationship were you really trying to capture in the first place? And should you have been controlling for those variables? That's never adequately really addressed. So I think let's get back to that.
Well, Aubrey, thank you so much. This is truly a provocative book. If you're interested in the history of statistics, if you're interested in probability theory, and if you're interested in, figuring out how to do science better, check out Bernoulli's Fallacy.
This is Unsilo, brought to you by Alumni FM, connecting people through stories.